Now, before we define the adjacency matrix, what I want to do is define a path. And luckily, we've already seen the definition of a path for a directed graph. So we'll rewrite this definition. We say that, and we have two separate but very similar definitions of path. One for a directed graph and one for an undirected graph. So for a directed graph, which is the more general of the two objects, a path from A to B is in G is a sequence of edges, and these edges are ordered pairs. We already saw this definition earlier when we were talking about Warshall's algorithm for closing a transitive or non-transitive relation. All the way up to xn minus 1 comma xn. The path is said to be x1 through xn minus 1 with the beginning point A and the final point xn b. So just an ordered sequence of edges. Typically we denote the path by just x0, comma x1, comma x2, all the way up to xn for short. The path has length n, because there are n edges in this path. If the edge set of a path is the empty set, then we say that this is a path of length 0. And lastly, a path of length n greater than or equal to 1 is called a circuit or a cycle. And now if our graph is a non-directed graph, our notation becomes a little bit less heavy because we don't need to use ordered pairs. So if we take a non-directed graph, the definition of a path is going to be word for word the same, but we can just use our definition of shortened definition of edges. So we say that it's edge x0, x1, all the way up to edge xn minus 1, xn. So there are still n edges in a length n path. And we still say that a circuit or a cycle if it begins and ends at the same vertex. Oops, I said it, but I didn't write it down. A path or circuit is said to pass through the vertices of the path and to traverse the edges. And lastly, we call a path simple or circuit is simple if it does not contain the same edge more than once. And so the next topic that I want to discuss is connectivity. This is going to be extremely important for talking about invariants of graphs as well as many other things. So just like we saw before, undirected graph is in some sense very different than a directed graph, and we have to be a little bit careful with how we define connectivity. So we'll start by defining connectivity of an undirected graph. And for our definition, we have that an undirected graph is said to be connected if there is a path between every pair of distinct vertices. We say that an undirected graph that is not connected is called a disconnected graph. So a disconnected graph is an undirected graph that is not connected. And with this idea, we can also then define what's called the action of disconnecting a graph. Specifically, we say that we disconnect a graph when we remove vertices or edges to produce a disconnected subgraph. So this brings up a new idea that we have to kind of define, and that's the idea of a subgraph. This is different than a subset. In some sense, it's stronger than a subset, because every graph is really, it's something that's more complicated than just a set. It's two sets, the vertex set and the edge set. So to correctly define a subgraph, we have to make this definition using both of these ideas. So we say that a subgraph of a graph G is a graph H with edge set F and vertex set W. So it's a different graph H, with a vertex set W and an edge set F, where W is in general a subset of the original vertex set. So the vertex set of this new graph is a subset of the original vertex set V, and F, the edge set of this new graph, is a subset of the original edge set E. I want to be a little bit careful here. Perhaps I shouldn't say new graph, because we've only used the subset here, right? We haven't used any idea of proper subset. So technically we could get that a subgraph is the graph itself. A graph itself is a subgraph of itself, because we only use subgraph or subset here. So we say that a proper subset or a proper subgraph is a graph in which the vertex set W is a proper subset of the original vertex set V, or the edge set F of this new graph is a proper subset of the original edge set E. In other words, this means that the graph G is not equal to the new graph H. Now, for directed graphs, we also have an idea of connectivity. However, we have to be very careful here. We have two different types of connectivity, what's called strongly connected and weakly connected. We say that a directed graph is strongly connected if there is a path from A to B and from B to A for all vertices A and B in the graph. Right, this is the definition of strong connectivity for a directed graph. And this is a different concept, right, from the definition of weakly connected for a graph. We call it strongly connected because it's more of a big argument or a stronger argument, or more of a condition that has to be held by a graph in order for it to be strongly connected. So the definition of weakly connected, and we say that a graph is weakly connected if there is a path between every two vertices in the underlying undirected graph. So every graph, every directed graph, has an underlying undirected graph that you can obtain if you just remove the directivity of the graph. So you remove all of the directed edges and just replace them with simple edges. So weakly connected is based on this idea. It's based on the idea of finding the underlying undirected graph and looking at if that is connected. This is both of these are very important concepts. So we're now going to shift our attention a little bit to one of the most important tools that we have in graph theory, at the beginning of graph theory, and this is called the adjacency matrix of the graph. And this can be defined for a multigraph, a directed multigraph, and so on and so forth. The adjacency matrix of a given graph is a matrix, so given a graph G, where the edge set is the multiset of multiplicities called Mij for each individual edge in the graph, Eij. Well, Eij, the edge connecting vertices Vi and Vj. So we say that the adjacency matrix of G is going to be a matrix. Specifically, it's going to be an n by n matrix, where V, number of vertices, is size n, and it's defined by Mij, the ijth component of this matrix, is going to be the number of paths of length 1 from Vi to Vj. And this is if Vi is connected to Vj and it's 0 otherwise. So this is a super important tool, and it gives us a great number of very interesting and neat results. Specifically, let's consider the following graph, and I'm going to show you that this can be used in a very specific way, in a very general way. Say we have the graph ABC, which is a mixed graph. So we have standard edges, we have a directed edge maybe, and we have a loop here, a loop on A, the most general type of graph. So the edge set here is the multiset, two simple edges from A to B, one simple edge from A to A for a loop. There's one simple edge from A to C. There's one simple edge from B to C. And there's one directed edge from B to C. So the matrix that is the adjacency matrix for this graph, and this can be computed in the exact same idea that we use for relations. So the 0, 1 matrices of relations, but now we just kind of write each one of our vertices along the rows and each one of our vertices along the columns, and we put the numbers into this graph that correspond to the walks of length 1 from vertex Vi to vertex Vj. So for instance, from A to itself there's one walk, because we can go along this loop. From A to B there are 2 walks. From A to C there is 1 walk. From B to A there is 2 walks. From B to B there are 0 walks of length 1. There's no loops here. From B to C there are 2 walks, because you can go along this one or along this one. From C to A there's 1 walk of length 1. From C to B there's only 1 walk of length 1, because you can't go in the opposite direction along this directed edge. And lastly, from C to itself there are 0 walks. So this is the correct adjacency matrix for this graph G. Now this is where I want to point out something very interesting. The idea here is that if you consider the directed graph that comes about by treating each one of these edges as an edge going in both directions. So this graph right here is graph G. Right here we'll consider this graph G prime. But we replace each one of the edges. You can do it with the loop as well, but I'm just going to do it with the directed edges. So we'll replace each one of the simple edges with two directed edges that traverse in opposite directions. So we keep this directed edge right here, and then this simple edge. We're throwing two oppositely oriented directed edges, and then lastly for this simple edge right here, we have two separate directed edges. And if you go through and calculate the adjacency matrix of G prime, you're going to end up getting the exact same adjacency matrix. So this is really cool and shows a deep connection between directed graphs, undirected graphs, or mixed graphs, and underlying undirected graphs. The idea here is that this is a super powerful tool for a general graph. And one of the first big theorems that we're going to prove with these graphs is what it means when we take the power of this matrix. So what the powers of the adjacency matrix mean. And keep in mind throughout all of this that this matrix, the adjacency matrix of a general graph, is going to be an element of the set of all matrices with entries coming from the positive integers or 0. This is n by n matrices, where n is the number of vertices. This is the mathematical set that we're working with here. So one of the coolest things that we can do with the adjacency matrix immediately after defining it is to go through and prove something about what the powers of this matrix gives us. So let G be a graph with the adjacency matrix M with respect to the ordering of vertices V1 to Vn of the vertices of the graph. With directed or undirected edges, with multiple edges and loops, all allowed. The number of different paths or walks, as they're sometimes called, of length R from Vi to to Vj, where R is a positive integer, equals the ijth entry of the matrix a to the power r, where this is normal matrix multiplication. This is a to the r minus 1 times a, where a to the 1 is just equal to the matrix A. And this is proved in a very straightforward manner using mathematical induction. Specifically, we have our base case, which is R equals 1, and by definition A to the 1 is equal to the adjacency matrix A, which is defined based on the number of walks of length 1 from all of the different vertices in the graph to all the other vertices in the graph. So our base case is really by definition. The inductive hypothesis is the hypothesis that there exists some R in the set of positive integers such that a to the r ij, the ijth component of a to the r, is the number of paths from vi to vj. And then our inductive step is to show that for all r in the positive integers, if the statement P of r is true, then statement P of r plus 1 must be true. So we assume our inductive hypothesis, and then we need to show that A of r implies, or A of r, if A of r is the number of paths from vi to vj, oops, and I should put of length r, then AR plus 1 is the number of paths from vi to vj of length r plus 1. So we assume our inductive hypothesis, and we look at A to the r plus 1. By definition, this is the matrix A to the r times A, and from our formula for matrix computation, we know that Cij, or better put, the ijth component of matrix A to the r plus 1 is going to be equal to the summation over the rows of A to the r times the columns of A. So just for computational simplicity, we'll call B A to the r, and A is just itself. This is going to be bi1 a1j plus bi2 a2j all the way up to bin a n j, where bij is the ijth entry in the matrix B. factors a to the r. And by the inductive hypothesis, because Aij is by definition the number of walks of length 1 from Vi to Vj, and Bij is, by our inductive hypothesis, the number of walks of length r from Vi to Vj. We're going to be able to show exactly what we want to show. So think about how a path of length r plus 1 is made up. Path of length r plus 1 from Vi to Vj is made up of two things: a path of length r from Vi to some intermediate vertex Vk, and an edge from Vk to Vj. This is true of any path of length r plus 1 from Vi to Vj. And by our product rule for counting, which was proved in an earlier lecture, the number of such paths then is the product of the number of paths of length r from Vi to Vk and the number of edges from Vk to Vj. And this is given exactly by definition by Bij. This is the number of paths of length r from Vi to some intermediate vertex. Oops, not Bij, Bik, times the number of edges from Vk to Vj. And this is, by definition, Akj. And then by the sum rule for counting, we have to add up this over every single possible edge, which is exactly the summation from k equals 1 to n of Bik times Akj, or the sum that we computed before when we computed the matrix product. So this concludes the proof. And so to show an example of this, I'm going to actually use an example from popular culture, specifically the movie Good Will Hunting. And in that movie, there's an MIT mathematics professor who gives the following problem to his class. G is this graph. Find the adjacency matrix A and the matrix giving the number of three-step walks in the graph G between all of the vertices in the graph. Now, 1 and 2 are within the realm of us doing right now. 2, 3, and 4, not so much, because we haven't talked about generating functions. But if you're interested, this is in chapter 8 of the book. This is an advanced method for counting, or combinatorics. Very, very useful. 3 and 4 also require a little bit more linear algebra than we necessarily have. So we're just going to stick with 1 and 2 here. So let's look at this graph. It's this graph right here. From vertex V1, V2, this is V2, this is V4, and this is V3. So the adjacency matrix that represents this graph you have V1 is going to be V2 and V4. V2 is going to be 1, V4, and V3 with 2 edges between V2 and V3. So we're going to have 1, a 0, a 2, and a 1. V3 is only connected to V2 with 2 edges. We have 0, 2, 0, 0. And lastly, V4 is connected to V1 and V2. So this answers part 1 of the problem, finding the adjacency matrix of this graph. To find the number of two-step walks between any two vertices, we have to look at mg squared, which is the matrix mg, multiplied by itself, so the first row times the first column, which will give us a 2, the first row times the second column, which will give us a 1, and so on and so forth to get 2, 1, 2, 1, 1, 6, 6, oh sorry, not 6, 1, 6, 0, 1, 2, 0, 4, 2, 1, 1, 2, 2, and then lastly, to get mg cubed, you write this as mg squared matrix multiplied by mg, or this matrix times the original matrix mg which, after computation, gives us the matrix 2, 7, 2, 3, 7, 2, 12, 7, 2, 12, 0, 2, 3, 7, 2, 2. This is part 2 of the problem. And this matrix directly matches up with the matrices that Will found in the movie. 2, 7, 2, 3, 7, 2, 12, 7, 2, 12, 0, 2, 3, 7, 2, 2. So the final thing that I want to talk about in this lecture is what's called a graph isomorphism, which is similar to the idea of a set isomorphism, but just like a subgraph is a more complicated structure, a slightly more complicated structure than a subset. A graph isomorphism will also be a more complicated structure than a set isomorphism, and it's going to use the idea of a set isomorphism. You see that two simple graphs are isomorphic, or graph theoretically isomorphic, if there exists a bijective function f from the vertex set, and we'll say that G1 here is our graph 1 with vertex set 1 and edge set 1, and G2 here is graph 2 with a vertex set 2 and edge set 2. They're just a bijective function from V1 to V2 with the property that if, or I should say if and only if, so A and B are adjacent in G1 if and only if f of A and f of B are adjacent in G2. And this is a very, very important concept in graph theory, because a lot of times if you draw down two graphs, you might wonder if they're isomorphic to one another. Sometimes you can prove that a given graph is isomorphic to a simpler graph, or a graph with a simpler looking structure. So this is a super, super important concept. One of the things that we can show is that the relation of being graph theoretically isomorphic is actually an equivalence relation. In terms of the real world applications of graph isomorphisms, we have applications in chemistry, the design of electrical circuits, bioinformatics, computer vision. Chemists use molecular graphs to model chemical compounds. Biologists use graphs to study structural isomers. It's extremely, extremely important in applications. And for large graphs, it's a very difficult problem. For small examples, it's relatively straightforward to go through and see whether or not they're isomorphic. But the idea is that showing whether or not two graphs are isomorphic for general number of vertices and edges is very, very difficult. There is good software and good algorithms out there, but they run in quasi-polynomial time, which is in a time where 2 is raised to the polynomial f of n, where f of n is a function that's log of n to the power 3. So it's slightly between polynomial time and exponential time. It's the best algorithm out there that is currently out there. It was invented in 2015. The best graphical general purpose software for isomorphism testing is called Naughty, N-A-U-T-Y, and can be downloaded and experimented with. However, so the problem of proving that two graphs are isomorphic is relatively complicated in general. However, proving that two graphs are not isomorphic is a slightly simpler venture. And the idea here is that what you do is to show that two graphs are not isomorphic, you have to find invariants between the two graphs that differ from one another. So let's define what an invariant is. A graph invariant is a property that is preserved by a graph isomorphism. So what I'm going to do is go through and just talk about a collection, a sub-collection of graph invariants. And I'm not going to prove that they're graph invariants, but it's relatively straightforward to do it and go through, and more details are in the book regarding proving this. However, the idea here that I want you to focus on, right, is that just because a certain number of graph invariants between two graphs match up and are equal, it doesn't necessarily mean that they are isomorphic to one another, because there are infinitely many graph invariants. So I want to emphasize that this list is not a full list, but these are some common graph invariants. First and foremost, the order of G, which is just equal to the cardinality of the vertex set. Right? If you have two graphs, one with more vertices than another, then they can't be isomorphic to one another. The size of G, which is the cardinality of the edge set of G, the multi-set. If the edge sets of two graphs don't have the same number of edges, then they can't be isomorphic to one another. The number of connected components is a good graph invariant if you can somehow show that your graph is really disconnected, or one graph is disconnected, and you have a different graph that is connected. These two things cannot be isomorphic to one another. generalized notions of distance to graphs, which we've done already, we say that the distance, or the length of a path is the number of edges in the path. So typically what we do is we say that the distance between two vertices is, we'll call these V1 and V2, is the length or number of edges of the shortest path between V1 and V2. And we denote this as d of V1, V2, because this is a function of the vertices, separate vertices in the graph. Using this concept of distance, we can define what's called the eccentricity of a vertex V, as we denote this as epsilon of V. This is equal to the maximum over all u vertices u in the graph of the distance between V and u. So the eccentricity of a vertex is the distance, or the length of the farthest path away from V in the graph. And using this idea, we can define the next invariant, which is the radius of the graph G. And the radius of a given graph is going to be the minimum over all vertices in V of the eccentricities. So you can compute the eccentricity of every vertex and then take the minimum of that set, and that will give you the radius of the graph. This is actually a min-max problem, because it's saying the minimum over V and V, the vertex set, of the maximum over U and U, or in V, of the distance between V and U. The diameter of a graph is defined to be the maximum over all of the vertices in V of the eccentricity function. Which is just the maximum over all U, V in the vertex at V of the distance function between V and U. Oops, and I just realized I left out of my list here something that is another big invariant, so I want to add this in here. This is neat that we have kind of a generalization of the idea of a radius and diameter to these general objects, to graphs. So for a general graph, we have that what's called the degree sequence is also an invariant. And this is just an ordered listing of the degrees of every vertex in the graph from high to low. For instance, if this is our graph, the degree sequence will be 3, 3, 2. So this is an important and relatively easy invariant to calculate. The last geometric inspired invariant that we have for a graph is called the girth of the graph. Okay, the girth of something is the thickness of something, and you see that the girth of a graph, this relates to cycles in the graph, this is equal to the shortest cycle length, or the length of the shortest simple cycle contained in the graph G. Right, and you can kind of understand how this kind of gives you a measure of the thickness of the graph, because the larger the girth, the larger the shortest simple cycle in the graph. So moving on from these geometric-like invariants, we're going to define some connectiveness invariants, or some invariants that relate to graph connectivity. And to do this, we want to define the idea of a vertex cut, an edge cut, and a separating set. So you say that a subset V prime of the graph G, which is the vertex set V and edge set E, is a vertex cut or separating set if G minus V prime, so we remove the vertices V from the graph VE. So the new graph that we get when we remove these vertices is disconnected. I want to note here that if we remove vertices, we have to remove the edges that are connected to that vertice. This concept leads to the graph invariant, known as the connectivity of the graph, or the vertex connectivity of the graph. This is kappa, Greek symbol kappa of G, and this is the minimum number of vertices needed for a vertex cut. So in other words, it's the smallest number of vertices that you need to remove to disconnect the graph. Note that for some graphs, such as complete graphs, or graphs that are fully connected, we can never disconnect the graph. So we also have to include that for a complete graph. Right? Then K of G, or K of Kn, the complete graph of n vertices, is just going to be n minus 1, which is the number of vertices that you need to get it down to one point. This is the highest value of the connectivity that we can have for vertex connectivity. We can also then go on and define almost the exact same concept, only with edges. We say that an edge cut of a graph, or a subset E prime, of a graph G is an edge cut or a separating set if the subgraph G minus E prime is disconnected. And this itself is another invariant. Specifically, we use the Greek symbol lambda to denote the edge connectivity of this graph. And this is the minimum number of edges needed for an edge cut. And we need to note here that the edge connectivity of a complete graph is going to be n minus 2. The number of edges in a complete graph, or a graph where all of the vertices are connected to all of the other vertices, is n minus 1. And therefore, the number of edges required to disconnect a complete graph, or not disconnect it, but turn it into a single vertex, is n minus 2. So we'll move on to some more invariants. These next invariants deal with coloring of a graph, which was described earlier. We'll define it more generally now. A coloring of a simple graph is the assignment to each vertex or edge of the graph are assigned the same color. And we have to be very specific here because now with this definition of coloring, there are actually multiple types of colorings that we can consider. It's called a proper vertex coloring, and without any qualification, right? If someone says coloring of a graph, typically they mean what's called just a vertex and only vertex coloring. But a vertex coloring of a graph G is a labeling or coloring of only the vertices, so that no two vertices sharing the same edge have the same color. And with this, we can define what's called the chromatic number of a given graph, which is an invariant. So when someone talks about the chromatic number, typically we use the notation chi of G, but I think a better notation would be chi naught of G, because we're going to talk about two other types of chromatic numbers as well. The smallest number of colors needed to color a graph to do a vertex coloring of the graph is called the chromatic number. And edge coloring of the graph G is a labeling of only the edges, so that no two edges sharing the same vertex have the same this property produces a graph invariant that is sometimes called the chromatic index. This is noted by chi 1 of G, or in certain references chi prime of G. And this is much like the chromatic number. It's the smallest number of colors needed to color G, or edge color G. And lastly, we can define the total coloring, and the total coloring is a type of coloring on the vertices and the edges of a graph. And when used without qualification, the total coloring is assumed to be proper in the sense that no adjacent vertices no adjacent edges and no edge and its end vertices are assigned the same color. And lastly, we can define the total coloring, and the total coloring is a type of coloring on the vertices and the edges of a graph. And when used without qualification, the total coloring is assumed to be proper in the sense that no adjacent vertices no adjacent edges and no edge and its end vertices are assigned the same color. And this concept leads to another invariant term, the total chromatic number. Which is denoted by chi prime prime of G or chi 2 of G. And just like the previous two, this is the smallest number of colors needed to total color G.